For this next series of videos, we're going to be talking about functions. What is a function? Well, put simply, a function is a rule that associates each input with a specific output. In this class, we're often going to see the rule written as an algebraic expression, like f of x. We can think about a function sort of like a vending machine. When we input something by pressing a button, we get a specific type of drink, which is our output. Each input, each button, corresponds to a specific output, a specific drink. So why are functions so important? Well, you've probably heard the term function being thrown around a lot in your previous math classes, but why are they discussed so frequently? Well, let's go back to our vending machine example. When we push a button on the vending machine, we want to know that the drink that we get corresponds to the button that we pushed. It would be a pretty bad vending machine if each button just dropped a random drink, or if pushing a button didn't give us a drink at all. We want to make sure that each input is perfectly mapped to a specific output. So with that definition in mind, which of the following diagrams depicts a function? That is, which of the following input and output pairs has it where each input corresponds to exactly one output? Well, for our first one, 1 corresponds with P. If we push a 1, we get a P. 2 corresponds with Q. If we push a 2, we get a Q. Great so far. What about 3? Well, if we push a 3, we also get a Q. Each time we push a button, we only get one specific output. It doesn't matter that 2 and 3 give us the same output, only that each button gives us one output. This is a function. What about the second one? The input 1 produces a P. Good so far. The input 2 gives us a P and a Q. When we push the button 2, we could either get a P or a Q or both. This fails. This is not a function, since it doesn't meet our definition. Every single input has to have only one unique output, and that is not true for number 2. Now, there are many different ways to represent functions. We've already seen a couple of them. And all of these different ways that we're about to describe are valid as long as each input can only have one output. Let's look at a few examples. The most often form we'll see in class is an expression. If our input is x, our output is 3x, as an example. This is a function that takes in a number and triples it. If I plug in the number 1, it will output 3 times 1. If I input the number 10, it will output 3 times 10. Each input only has one output, so it's a function. Another way to express a function is with a graph. A graph is just a collection of inputs, which are on our x-axis, and outputs expressed along our y-axis. We'll see that when the input is 1, the output is 3, and we mark that with a point at 1, 3. If we pick a different point, like an input of 2, our output is 6, and we mark that point 2, 6. If we look at all the points that satisfy the same condition, we can see that this line represents the same function we were looking at before. It takes in our input and triples it. When we're working with real-world data, we'll often have a table representing a function. Now we'll notice this is a different function than before. It does not take in our input and triple it. However, we could still represent this as an equation or as a graph if we plotted all of these points. Notably, this is a function because for each of our inputs here, they're mapped to only one output. -3 is always mapped to -1. 0 is always mapped to 1, and never anything else. So although this is a different function than before, it is still a function. This would fail as a function if, for example, 0 was also mapped to 0. 0 is already mapped to 1. It can't be mapped to another thing. Each input can only have one output, not two. When we're communicating, we often represent functions without even thinking about it. For example, if the price of a coffee is $3 for a small and $4 for a large, we're dealing with functions when we say, I would like 2 small and 1 large coffees. We could call S the number of small coffees, and we could call L the number of large coffees. And if I said, how much would it cost for 2 small and 1 large coffees? Well, we could say that the cost equals 3 times the number of smalls plus 4 times the number of large. So if we have 2 small coffees and 1 large coffee, then the cost would be 3 times 2 plus 4 times 1. And this formula will work, this function will work, no matter how many small and large coffees we're getting.